Alright, in this video we'll continue on 5.2 and we're going to talk about covariance and correlation in this video. First of all, let's take a look at the covariance. So when two random variables x and y are not independent, it is frequently of interest to assess how strongly they are related to each other. So if they're not independent, we'll say, okay, there is a relationship between those two random variables, and we want to see how strongly they're related, or what kind of relationship is between those two random variables. All right, let's take a look at the definition of covariance here. So the covariance between two random variables is equal to, so we use COV of x and y represent covariance. The covariance of x, y is equal to the expected value of x minus the mu of x, mu sub x, times y minus mu sub y. So since actually this is this is an expectation, and based on what we learned in the previous video, we know that the expected value of h of x y, so this would be equal to double integration negative infinity to positive infinity, negative infinity to positive infinity, h of x y times the joint PDF dx dy, right? Of course, this is for x and y are continuous. But if this is for continuous, if the two variables are not continuous, or if the two variables are discrete, we're going to have this would be the double summation over x and y, and then h of x y times the joint PMF of x, y, like that. So same idea here. So the whole thing instead of expectation here, x minus mu x and times y minus mu sub x. So we can consider this whole thing instead as a function of h of x, y. And then of course we can figure out this expectation by applying the formula here. So if x and y are discrete, we're going to have double summation, the inside of the expectation multiplied by the joint PMF. And if they are continuous, so we're going to have the inside of the expectation times the joint PDF and then dx dy. So that's how we find this expected value. That is, since x minus mu sub x and y minus mu sub y are deviations of the two variables from their respective mean values, the covariance is the expected product of deviations. Note that the covariance of x and x, basically the covariance of x itself, is going to be equal to, so based on the formula here, we're going to have, if we have the covariance x and x, so we're going to have this is equal to E of x minus mu sub x times x minus mu sub x. Okay, the reason why we did this two times is because we got two x's in the covariance. So this would be equal to E of x minus mu sub x squared. So based on the definition of variance, so this would be equal to the variance of x. Okay, so basically the covariance, in other words, the covariance of two same variables is equal to the variance of this variable. Okay, that's what it's really talking about here. All right, now let's take a look at how the covariance will tell us what kind of relationship that two random variables have. Okay, so let's take a look at what it's talking about here. The rationale for the definition is as follows. Suppose x and y have a strong positive relationship to one another, so by which we mean that the large values of x tend to occur with large values of y, and the small values of x with small values of y. So which means if there's a positive relationship between x and y, we're going to see that if x increases, then y increases. If x decreases, then y decreases. That's what it's talking about here. So the most of the probability mass or density will be associated with x minus mu sub x and y minus mu sub y. So either both positive, so both x and y above their respective means, or both negative, so the product will be positive. Thus, for a strong positive relationship, covariance of x and y should be quite positive. So in other words, if the covariance of x and y is positive, then we can see the relationship between x and y is positive. Okay, That's what we got from here. And then for a strong negative relationship, the signs of x minus mu and y minus mu will tend to be opposite, yielding a negative product. Thus, for a strong negative relationship, the covariance of x and y should be quite negative. So which means if we have the value of the covariance is negative, then we can say that there is a negative relationship between x and y. Okay, which means when x increases, y decreases. If x decreases, y increases. Okay, and then if x and y are not strongly related, positive and negative products will tend to cancel one another, yielding a covariance near zero. So we're going to have the figure 5.4 down here illustrates the different possibilities. The covariance depends on both the set of possible pairs and the probabilities. In figure 5.4, the probability could be changed without altering the set of possible pairs. And this could dramatically change the value of covariance of x and y. Now let's take a look at the graphs over here. Now we can tell that we on the x coordinate we have the mu sub x, so which is average value of x, and the mu sub y on the y coordinate, which is average value of y. Okay, so if we draw a horizontal line and a vertical line from the mu sub y and mu sub x, so we're gonna have 4 quadrants over here. Okay, so for quadrants over here, we're talking about the product of x minus mu sub x times y minus mu sub y, right? Now, in the first quadrant, we can tell all of the x values in the first quadrant is greater than mu sub x, okay? And all the values in the first quadrant are greater than the mu sub y. So which means both of them are positive. The product will be positive. This sign is the product of those two things. And then let's take a look at the third quadrant over here. So for all the outer pairs in this quadrant, we can tell all of the x values are less than mu sub x, right? Then which means this part is negative. And then all of the values are less than mu sub y. So which means this part is negative as well. So negative times negative will give us the positive. So in other words, on the other side, those two, the outer pairs in the second and the first quadrant will give us the product is negative. So in this case, we'll say that the relationship between x and y is positive. Actually, technically, we can tell that this is like a roughly straight line here, and it's kind of increasing, which means when x increases, y increases as well. When x decreases, y decreases as well. That's why we say there is a positive relationship between x and y here in this case. Okay. All right, let's take a look at the second graph over here. Actually, from the view of the graph, we can tell this is a decreasing line. So which means, it's not decreasing line, it's a decreasing trend, okay? Which means when x increases, y decreases. When x decreases, y increases, okay? Now we can tell that, for all of the points in the second quadrant over here, we can tell that all of the x values are less than mu sub x, so which means x minus mu sub x would be negative, and all of the y values in this part would be greater than the mu sub y. So this part is positive. Negative times positive will get negative sign here. Okay, and then in the fourth quadrant, we can tell all of the x values in this part are greater than mu sub x. Then we have x minus mu sub x is positive because all of the x values are greater than mu sub x. And then all of the y values are less than mu sub y, right? So we have x minus mu sub y is negative. And then we have positive times negative give us negative here. Okay? And in this case, we'll see that there is a negative relationship between x and y in this case. All right. In the third case, we can tell actually there is not a trend. We cannot tell whatever a positive or negative trend from the graph number 3. Then we will see that in this case the covariance of x and y is roughly equal to 0. Okay. I wish that makes sense to you based on the graph and the statement over here. Okay, so once this makes sense to you, let's take a look at how to find the covariance of x and y. So basically what we need to do is just we need to identify if we're dealing with the random variables or discrete random variables. Once we got that, we just need to apply the formula given here, and that's it. All right, just take a look at that. So the joint and marginal PMFs for x is equal to automobile policy deductible amount, and y is equal to homeowner policy deductible amount, exact 5.1. So this is a continuation of 5.1. So we got this joint probability distribution and the marginal probability distribution, right? So if we want to find, since in this case x and y are discrete, so we want to apply the formula COV, the covariance x and y is equal to expected value of x minus mu sub x times y minus mu sub y. We need the bracket here, and then that would be summation over x, summation over y, and then x minus mu sub x times y minus mu sub y times the joint PMF of x and y. So that's the formula we want to apply here. So basically, we have already known the joint PDF from the joint probability distribution, and then we need to find the mu sub x and mu sub y first. So of course, if we want to find the mu sub x, that would be equal to the sum of x times the marginal PMF of x, which is so that would be 100 times 0.5 plus 250 times 0.5, and then we get the answer is 175. The same thing for the mu sub y, so that would be equal to summation of y times mu sub y. Not mu sub y times the marginal PMF of y. So in this case, that would be 0 times 0.25 plus 100 times 0.25, and then plus 200 times 0.25, and then you will get the answer 1.25. And then once we got both mu x and mu y, so we just need to plug it back into this formula here. So the summation over x and y, x minus mu sub x, which is 175, times y minus mu sub y, which is 125, times the marginal the joint PMF here. And then we can tell, so when x is for the first order pair, x is 100, y is 0. X is 100, y is 0, and the joint probability is 0.2. So that we have x minus mu sub x, which is for the first order pair, that would be 100 minus 175, and then times y minus mu sub y. So this would be the y value of the first pair. So in this case, the value is 0, 0 minus 125, and the corresponding probability of this other pair is 0.2. Okay, and that's why we multiply by 0.2 over here. And then for the very last pair over here, we have, for this pair, x value is 250, y value is 200, and the corresponding probability is 0.3. So that's why we have 250 minus 175, which is mu sub x, and times the y value 200 minus mu sub y times the corresponding probability, which is 0.3. So of course we need to do this thing for all the 6 pairs over here, and then you add them all up, you will have the covariance is 1875. Okay, I think for the calculation part is pretty straightforward. Okay, and the following shortcut formula for covariance simplifies the computations. So this is a shortcut version of the formula of the covariance. Now let's take a look at how we got this formula over here. We know that the covariance of x and y is equal to the expected value of x minus mu sub x times y minus mu sub y, right? And then what we want to do next is we just need to expand the inside of the expectation. So that would be x times y will give us x and y, and then x times negative mu sub y. That would be minus x mu sub y. And then negative mu x times y will give us minus y times mu sub x. And then negative mu sub x times negative mu sub y. So negative times negative give us positive, and then mu sub x and mu sub y, right? And then based on the property of expectations, we can just break this thing into 4 parts based on the additive property. So that would be e of xy minus e of x mu sub x minus e of y mu sub x plus e of mu x mu y. And then the key point here is that we know that both mu x mu y are constant. They're constant numbers. Mu x mu y are constant numbers, and of course if mu x mu y are constant, then the product of mu x mu y is constant as well. And then if we have constant numbers inside the expectation, we can pull it out of the expectation directly. So based on the linearity of the expectations. So we have e of xy minus e of x times mu sub y minus e of y times mu sub x, and then plus mu sub x mu sub y. Okay? And then e of xy, we don't have to change that. What is e of x? E of x is just mu sub x, right? Times mu sub y minus e of y just mu sub y, right? Mu sub x. And then plus, we just rewrite the last part, mu x mu sub y. So those two will cancel out, right? Negative mu sub y mu sub x plus mu sub x mu sub y. So those two will cancel out, and then we will have the covariance of xy is equal to e of xy minus mu x mu y. So actually, once we have this, we're going to have, if we want to apply this formula, we need to find e of xy first, and then mu sub x and mu sub y by applying the formula we went over before. So e of xy, of course, is going to be equal to, if it's continuous, so we do the double integration. Double integration, of course, x of y, f of x and y, dx dy for the continuous. And then for the discrete, we're going to sum over x, sum over y, x and y times the p of x and y for discrete, of course. Discrete. And then of course, mu sub x would be equal to negative infinity to positive infinity, x f of x dx is continuous, and the sum over x times p of x for discrete. Of course, same thing for mu sub y, right? So we just need to figure out those 3 things separately, and we use e of xy minus the product of mu x mu y, so we get the covariance. All right, so once this clear, just let's take a look at this example here. This is a continuation of example of 5.5. It says the joint and margin of PDFs of x is equal to amount of almonds, y is equal to amount of cashews, and we have that the joint PDF is equal to 24xy, and x is between 0 and 1, y is between 0 and 1, and x plus y is less than or equal to 1. And based on the previous calculation we did before, we have the margin of PDF of x is 12x times 1 minus x squared when x is between 0 and 1. And of course, we can calculate both mu x mu y by doing the integration. This is equal to the mu sub x is going to integrate, of course, since the interval of x is 0 to 1, and the x f. We can calculate the mu sub x and mu sub y by applying this kind of formula. So after calculation, we'll have this is equal to 2 over 5. I think we did this in the previous video. I don't remember precisely, but I remember we did something like this in the previous video. But anyway, this calculation is kind of easy. So once we get both mu sub x and mu sub y, we just need to find e of x, y, and then we can apply this formula here. We have already got the mu x, mu y, right? So if we have the e of x, y, we can calculate the covariance of x, y. So based on the definition, we have e of x, y is going to be equal to double integral negative infinity, positive infinity, x, y times f of x and y. And I will draw the picture again for the positive density region. This is a 0, x and y. So we have, first of all, we have both x and y between 0 to 1, and this line is y is equal to 1 minus x. Okay. Of course, if we fixed x value, and the y value should be between 0 to 1 minus x. Because since this boundary here, we're gonna have that the value will depends on the exact value of x. Okay, of course, if this is an x, and then the upper boundary of y would be 1 minus x. It cannot be higher than that. If it's higher than that, it would be outside of this region, which is not what we want here. And that's why the boundary is for x is from 0 to 1, and for y is from 0 to 1 minus x. Okay, that's the reason why I mentioned this again and again. I just want to let you know that this part, draw the region and find the boundaries of x and y, is super important. Super important. You would definitely see something like this on both the exams. I mean, for the second exam and the final exam, and on the homeworks. So once you got the boundaries, I think it's the calculation part is quite easy. So what we need to do, just combine like terms. So we're gonna have 24x 24 x squared and 24x squared y squared, right? And then we do the integration with respect to y first. That would be x squared, from 0 to 1 minus x, and then dy. So we're going to have 8x squared, and then y cubed from 0 to 1 minus x, and then we plug both the upper and lower bound back into here for y. We're going to have 8x squared times 1 minus x, and then cube. And that's what we got inside of here. And then the 8 is, since 8 is constant number, it pulled out of the integration. And then you just need to spread it out and then finish the calculation part. And I think this is the calculation part is not too hard to figure out, but the final answer would be 2 over 15. Okay. So once we got the value of e of x, y, we can just apply the formula e of x, y minus mu sub x times mu sub y. So which is 2 over 15 minus 2 over 5 times 2 over 5, because that's the value of mu x and mu y. And then we get the covariance is negative 2 over 75. Since the value is negative, so we will see that there is a negative relationship between x and y in this case. Okay. All right. Once this is clear, I think once we know the proposition or the formula we went over up here, I think the calculation part is quite easy. Okay. All right. So once this is clear, let's take a look at the statement over here. Now, so based on the previous calculation we did, we got. It might appear that the relationship in the insurance example is quite strong, since the covariance is 1,875, whereas the covariance of x and y in this example here is kind of low, because the value here is kind of close to 0, which is equal to negative 2 over 75. In the not example, which seem to imply quite a weak relationship. Unfortunately, the covariance has a serious defect that makes it impossible to interpret a calculated value. So in the insurance example, suppose we had expressed the deducted amount in cents rather than in dollars. Then 100x would replace x and 100y would replace y, right? Because we used to express the amount in the terms of dollars, but now if we want to do it in terms of cents, so each number would be get multiplied by 100. So we are looking for the resulting the covariance we are looking for would be the covariance of 100x and 100y, right? And then if we pull out based on the property of the covariance, we can pull out the constant numbers outside of covariance. That would be 100 times 100 and times the covariance of x, y, and we'll get this thing here, this number, this big number here, which is 10,000 times of the covariance we got above here. But actually we didn't change anything else but the unit of the money here. And if on the other hand the deductible amount had been expressed in hundreds of dollars, the computed covariance would have been 0.01 times 0.01 times that, which is 0.1875. So basically this is like 10,000 times smaller than the original value we got before. But same thing here, we didn't do anything new, but only change the unit. Okay, now let's say the defect of the covariance. The defect of covariance is that its computed value depends critically on the units of measurements. Ideally, the choice of units should have no effect on the measure of strength of relationship. This is achieved by scaling the covariance. Okay, so before talking about scaling the covariance, I just want to phrase this, which is that the covariance can only tell us the sign of the relationship between x and y. The sign of the relationship between those two random variables. So based on the covariance we get, we can only tell if the relationship is positive or negative. That's all we can get from the covariance. Okay, we cannot say how strong the relationship is by only looking at the covariance. All right. So, but once we scale the covariance, we can do that. We can see how strong the relationship is between two variables. Now let's take a look at how to scale the covariance. And this brings us to the definition of correlation. Definition: the correlation coefficient of x and y denoted by COOR xy, and we usually use the rho sub x and y, or just rho. It's defined by the correlation coefficient is equal to the covariance of xy divided by the standard deviation of x times the standard deviation of y. Okay, now actually we can do this we can calculate this thing very easily, because we know that the covariance of xy is equal to e of xy minus e of x times e of y, right? That's what we get in the first part of this video. And then sigma x would be equal to the square root of the variance of x, right? And we know the variance would be equal to e of x squared minus the quantity square of e. And then of course we have e of x squared would be equal to, if it is continuous, that would be negative infinity, positive infinity, x squared f of x dx. Of course, e of x would be equal to negative infinity to positive infinity x times f of x dx. Okay, so for the standard deviation of y, that would be the same thing. Okay, we just need to replace the x, with y, in those two integrations here. So all right, let's take a look at example here. It is easily verified. In the insurance scenario of example 5.15, the e of x squared it's going to be equal to this, and the variance is going to be equal to that, and the standard deviation is going to be 75, which is the square root of this number, of course. And the e of x squared is going to be equal to this, and the variance is equal to that, and the standard deviation is equal to that. So once we have all those numbers, we just need to plug it back into this formula over here. Okay, so I wouldn't go over the calculation here because I don't know how many times we have done this before. So we know how to find, e of x squared and e of y squared, and we know how to find the expected values as well. So I wouldn't go over the calculation part again. I just show you how to do it over here and how to apply this formula. Basically, you just need to calculate those three things over here, and then plug them back into this formula. We'll get the correlation coefficient. Now, once we know how to calculate the correlation coefficient, let's take a look at how the correlation coefficient will explain the relationship between those two random variables. So the following proposition shows that rho remedies the defect of covariance xy and also suggests how to recognize the existence of a strong linear relationship. Okay, I just want you know that I get emphasize the word linear here because the correlation coefficient only explain how strong the linear relationship is between those two random variables. Okay, it cannot explain any other relationships. So based on the functions you learned before, we know that the function could be linear function, could be quadratic function, could be polynomial, could be exponential, or something like that. But over here, the correlation only explains how strong the linear relationship is. Okay, now let's take a look at the proposition here. If A and C are either both positive or both negative, then the correlation of ax plus b and cy plus d is equal to the correlation between x and y. Okay, for any two random variables x and y, the correlation coefficient is always between -1 and +1. The statement 1 says precisely that the correlation coefficient is not affected by a linear change in the units of a measurement. So if, say, x is equal to temperatures in Celsius, then 9x over 5 plus 32 is the temperature in Fahrenheit. Okay, but that wouldn't change anything, right? This is just a different units. According to statement 2, the strongest possible positive relationship is advanced by rho is equal to +1. Whereas the strongest positive negative relationship corresponding to rho is equal to -1. So I wouldn't go over the proof over here in the lecture videos, but if you are interested in it, you can take a look at the exercise 35 in the textbook. Okay, I wouldn't go over it again, but I would like to emphasize is this, the descriptive purposes. So the relationship will be described as strong if the absolute value of rho is 0.8. If the moderate if the absolute value of rho is between 0.5 and 0.8. And it's weak if the absolute value of rho is less than or equal to 0.5. Okay? That's how we describe the strength of the linear relationship between those two random variables. All right, so once this is clear, let's just take a look at this proposition here. This would be the very last part of this video. So if x and y are independent, then rho is 0. But rho is equal to 0 does not imply the independence. Okay? So what does it mean? So if x and y are independent, we will say there is no relationship between x and y. So whatever kind of relationship, no, there's no relationship. Of course, we will say there is no linear relationship between x and y. If there is no linear relationship between x and y, then rho is equal to 0. But if rho is equal to 0, which means if the correlation coefficient is 0, then we will say there is no linear relationship between x and y, but there could be some other kinds of relationships. That's why we say that rho is equal to 0 does not imply the independence. Okay. Once again, the the value of the correlation coefficient only explains the strength of the linear relationship between x and y, only for linear relationships. All right, for rho is equal to 1 or negative 1 if and only if y is equal to ax plus b for some numbers a and b with a is not equal to 0. So basically, if we have y is equal to a, if we have y is equal to ax plus b, we have that there is a perfect linear relationship between x and y, right? If there is a perfect linear relationship, of course, it could be, the rho could be positive or negative. It depends on the sign of a. If a is negative, then rho is going to be negative 1. If a is positive, then rho is going to be positive 1. Okay. Now let's go over the statements down here for quick. So this proposition says rho is a measure of degree of linear relationship between x and y, and only when two variables are perfectly related in a linear manner will rho be as positive or negative as it can be. A rho less than 1 in absolute value indicates only the relationship is not completely linear. Okay, but there may be a very strong non-linear relation. Also, if rho is 0, does not imply that x and y are independent, as what I just mentioned, but only that there is a complete absence of linear relationship. Okay, when rho is 0, x and y are said to be uncorrelated. So if rho is 0, we say they are uncorrelated, but we don't say they are independent. Two variables could be uncorrelated yet highly dependent because there is a strong nonlinear relationship. So be careful not to conclude too much from knowing that rho is equal to 0. So once again, rho, the value of rho or the value of the correlation coefficient only explains the strength of the linear relationship between x and y. All right, I wish this makes sense to you, and that's all about this video.